Okay, I will collect your homework after we go through some questions in your homework, and then we're gonna finish up the rest of the chapters. Chapter 3. 우리 숙제 다 끝냈어? 어려웠어? calculation 문제들 이번 방학 때 조금 타이트하게 잡아보자 했을 때. 왜냐면 뭐 나올 거고 계속, 그리고 계속 어려울 거야. 더 어려울 거야. 지금 막 이러더라고. 지금보다 더 어려울 수 있어요? 그럼요. HSA 2021년도 문제를 내가 한번 줄 건데, 한번 그 문제가 근데 원픽이야. 제일 어려운 문제야. 그 역대 HS 문제 중에서 와, 이 문제 진짜 어렵다 생각하면 진짜 어려울 수 있겠다 생각하는 문제였는데, 근데 생각보다 하다 보면은 이거 할 수 있겠다는 생각 바뀌는 게 중요해. 이번 방학 때 목표가 그거고, 그래야지 우리가 다음 모듈 7 끝낼 거고, 모듈 학교에서 모듈 5 시작한댔나 하지? 진짜 이상해. 우리는 모듈 8을 웬만큼 다음 텀까지 해서 다다음 텀까지 다 끝낼 생각이긴 해. 그러고 나서 모듈 7은 좀 프랙티스를 많이 할 거고, 왜냐면 너희가 이제 외워야 되는 게 되게 많거든. 알다시피. 정말 외우게 해줄 거야. 그래서 외우게 시험도 볼 거고, 계속 어떻게 설명도 계속 해줄 거고, 계속 노출시켜 줄 테니까 확실하게 외우고, 나중에 이제 트라이얼 준비를 우리가 언제부터 할 거냐면은 텀 3에 시험 보거든. 텀 3 week 1, 2에 이제 시험을 볼 거야. 그러면은 우리는 트라이얼 준비를 적어도 텀 2 week 6에는 시작을 해야 돼. 6, 7에는 시작을 해야 돼. 그래야지 6, 7, 8, 9 혹은 7, 8, 9, 10 4주 하고, 그 다음 2주 동안 또 이제 그 방학 동안 하고, 그 다음부터는 수업이 없을 거예요. 왜냐면 너 시험 준비해야 되니까. 그거 트라이 끝나고 다시 올 거야, 바로. 트라이 기간 동안은 안 와도 돼. 혹시 근데 나중에 한 번 더 얘기를 하겠지만, 너희가 궁금한 게 있으면은 이거 좀 모르겠구나, 아니면 프랙티스 문제가 더 필요하거나 그러면은 그때 와서 나한테 받아가거나 물어보거나, 그거는 따로 오픈해서 하면 되는 거니까. 했을 때 그게 일종의 애뉴얼 플랜이야. 왜냐면 그 전까지 물론 어세스먼트 나올 거고, 시험 나올 거고, 프랙티컬 타스크 나올 거고 할 건데, 계속 그거를, 특히 12학년은 애뉴얼 플랜을 좀 너희가 짜고서 움직이는 게 좋아. 그래야지만 너희가 숨을 쉴 수가 있어. 아니면은 어떤 느낌이냐면은, 수영장에서 이렇게 물 먹어본 적 있어? 막 다리 쥐나거나 아니면 해가지고, 그러면은 나는 계속 위로 올라가는데 물을 계속 먹는 느낌이잖아. 그 느낌이야. 그게 정말 살려고 막 발버둥 치잖아. 근데 생각해봐. 살려고 발버둥 치는데 실제로 수영을 하는 건 아니야. 그러니까 너희가 막 수영이 늘거나 아니면은 뭐 이렇게 앞으로 나가진 않아. 그냥 그 자리에서 살려고만 이렇게 발버둥 치는 것뿐이야. 근데 적어도 내가 어딜 가야 되는지 알고 어떻게 준비를 하고 있으면은 갈 수 있단 말이지. 그러니까 그거를 좀 유념해 두고, 12학년이니까. 참 재밌지 않아? 작년 이번 방학 때는 너 13년이었거든. 그리고 막 그렇게 스트레스 많이 안 받았을 거거든. 이제 11학년 시작한다. 왜 이런 일이 있어. 시니어 타이 받아요. 저 막 좀만 있으면 jersey 받아요. 막 너무 I'm so excited. Like I'm getting some jersey. 막 이랬는데 항상 1년만 지나보자. 그게 1년이 딱 지나니까 엄청나게 상황이 바뀌었죠, 했을 때. 근데 한 가지 더. 내년 이맘때쯤에는 내년 이번 방학 때는 진짜 너무 좋을 거야. 물론 대학교 오퍼가 나오면. 대학교 오퍼는 그것도 말씀해 주세요. 저희가 HSE 오퍼가 리설트가 언제 나오면은 12월 20일쯤 나와요. 크리스마스 한 일주일 전 정도에 나와. 야, 그러니까 생각해 봐. 너 특히 내가 너희 어머니라니까. 점수가 잘 나오면은 세상 그 어느 때보다 내 이쁜 딸. 와, 세상 어느 때보다 "야, 우리 너무 좋다." 막 하면서 오늘 막 뭐 먹을까 외식하고 막 용돈 받고 심지어 막 대학교 오퍼도 나오거든. 막 그냥 이런 네임 밸류 있는 대학교 갔어. 막 UNSW 혹은 막 UC 들어갔어. 그리고 한국 가. 그러면은 진짜 그 삼촌, 이모 막 다 용돈 줘. "와, 다 수고했다." 수험생, 한국의 수험생 생각하니까 수고했다." 막 이렇게 용돈 막 찔러 줘. 막 이렇게 10만 원, 많이 받으면 20만 원 "가서 놀아." 누구도 공부하라는 소리 안 할 거고 누구도 너를 잘했다고만 얘기를 할 거고 뭐 세상에서 그런 경험이 별로 없거든. "야, 잘했어. 고생했어." 이런 경험을 이렇게 cheer up 받는 기분을 그게 정확하게 내년 이맘때쯤이야. 그리고 막 친구들과 놀러 나가 이쁘게 꾸미고 화장도 하고 뭐 화장품 사러 가고 뭐 일도 하고 막 남자 친구도 뭐 생기겠지. 그때쯤 되면은 막 연애도 하고 그래도 누구도 뭐라 하지 않아. 혹은 누구 사람들이 했을 때 "그래, 너는 그럴 수 있어. 넌 그럴 자격이 있어." 근데 반대로 생각해 봐. 점수가 안 나왔어. 막 진짜 89 막 이렇게 나왔어, 에이타가. 뭐 나 89은 난 에이타라고 생각하지 않아요, 솔직히 말하면은. 90 above는 좀 돼야지 그 어느 정도 너희가 원하는 대로 할 수 있을 거고 생각을 할 수 있을 테니까. 95 이상 나왔어. 97 나왔어. 와, 근데 이제 막 89 나왔어. 그러면은 진짜 집안에서 막 "아유, 저거는 내가 돈을 갖다 들인 쳐드린 돈이 얼만데 내가 지금 과외하고 학원 보내기 위한 돈이 얼만데." 막 이런 말부터 시작해 가지고 하고 가면은 "어디 갔니?" 그 네가 되게 쪽팔려 가지고 어디 갔는지도 얘기를 못 해 스스로 막 이렇게 쭉 울어들어 이렇게. 한국 가기 싫어요. 나 삼촌 집 가기 싫어요. 그런 스트레스가 생각해 봐. 그거는 최악이야. 인생에서 그런 스트레스를 받기 시작하면은 야, 그건 평생 가. 왜냐면은 그 삼촌에 대한 안 좋은 기억만 남아 있어 이제. 난 삼촌 집에 가 가지고 그때 대학교 1 학년 때 막 그랬으니까. 그러니까 그런 것들을 우리가 잘 생각해 봐요. 앞으로의 너희가 하는 하나가 크지 않아. 진짜 하나, 딱 하나. 뭐 너희가 안 한다는 게 아니다. 너희는 한 애들이니까. 자꾸 얘기하면은 안 한 애들은 내가 이렇게 얘기도 안 해. 한 애들은 그냥 하자. 한마디 딱 해. 너희가 하니까 쪼끔 더 한 스텝만 더 하면 될 것 같아. 많이도 아니야 지금은. 정말 한 스텝만 더 하고 한 개 더 있으면 한 번 더 하고 한 번 더 하고만 하면 돼. 그것만 하면 돼. 시간 좀 남잖아 솔직히. 막 그렇게 24 시간에서 에서 막 16 시간 공부하지 않잖아 현재 상황에서는. 근데 그럴 수밖에 없는 상황이 트라이얼이야. 그럴 수밖에 없는 상황이 HSC보다는 트라이얼 때 공부를 더 많이 한다 참고로. 아이러니하죠. 왜냐면 HSC 그땐 내가 한 번 더 얘기를 해 줄게. "얘들아 정신 차려." 트라이얼 끝나고. 트라이얼 끝나고 나면은 내가 지금 애들 기다리면서 이런 얘기하는 거다. 지금 2 명이 안 와 가지고 올 것 같으니까. HS 끝나면은 트라이얼 끝나면은 얘들이 진짜 이상해. 다 끝난 것처럼 놀아. 나는 딱 그래요. 그 트라이얼이 정확하게 금요일 날 끝난 애들도 있는데 아닌 애들도 있어. 예를 들어서 트라이얼이 수요일 날 끝났어. 그러면 학교 너희 안 가도 돼, 목, 금. 다 exam period니까. 4일 동안 목, 금, 토, 일 있지? 진짜 내일이 없는 것처럼 놀아. 공부하지 마, 그땐. 왜냐면 미쳤다고 내가 공부하라고 앉아 가지고 너희가 앉아서 공부하겠니? 무슨 공부를 할 거야? 트라이얼 끝났는데. 이런 느낌이 있잖아. 그러니까 4일 동안은 그냥 즐기고 나는 공부하지 않아도 된다는 그런 어느 정도의 그런 뭐랄까 인슈어스 있으니까 그냥 부모님한테도 얘기를 해. "나 4일 동안 놀 거야." "Hi Ashley." 그 놀고 대신에 딱 4일 놀고 다시 돌아와야 돼. 그거를 내가 뭐라 하냐면은 resilience라 하거든. 그 빨리 돌아온 친구들. 그거를 빨리 돌아온 친구들하고 빨리 안 돌아온 친구들의 차이가 이만큼 벌어지기 시작해. 그게 HS에서 마킹 이제 붙여 놨다. 텍스트 나온 얘들 거 봐봐. 작년 거 보면은 어세스먼트 마크가 있고 보면 exam 마크가 있잖아. 지금 보면은 그리고 overall이 있어요. 이거를 테이크하는 거야. A타임은 overall을. 어세스 마크는 다른 말로 하면 인터널이야. 트라이얼은 여기까지밖에 안 들어가. 트라이얼 그러니까 랭킹 정하려고 트라이얼 보는 거야. 랭킹 정하고 나면 이거 끝이야. 그러니까 애들이 나 HS 끝났어요 생각하는데 아니야. 인터널 이제 반 온 거야. exam을 그리고 이런 경우 있다니까. 잘해가지고 랭킹 잡았어. 막 랭킹 third, second, so you got a 92 이렇게 나온 얘가 있어. 근데 진짜 아까 말한 것처럼 트라이얼 끝나고부터 갑자기 나는 인생의 모든 공부가 끝났어요 하고 공부를 안 한 애들이 있단 말이야. 그러면 진짜 놀아. 와 12학년 저렇게 놀아도 돼? 라고 좀 놀아. 내가 어떻게 하냐고 저지 입고 놀아 애들이. 저지 입고 막 노래방 가고 저지 입고 막 CC 나가고 막 놀고 있어 이렇게 막. 내가 대학교 있을 때도 대학교에서 막 저기서 막 연애질 하고 있어 거기서. 론야드에서. USD 거기 론야드가 앞에 있잖아. 좋잖아. 넓고. 그러니까 거기서 막 뒹굴고 있어. 그럼 생각하는 거지. 그리고 그런 애들은 어떻게 나오냐면 exam이 한 80 그러니까 좀 안 했으니까 86 이렇게 나올 때가 있어요. 이것만 봤을 때는 맨6지. 둘이 합쳐서 평균 내용 뭐니? 88이야. 아닌가? 89인가? 89이네. 밴드가 이렇게 나오죠? 밴드 나와요. 참고로 밴드. 참 살벌하죠? 밴드 5예요. 이러면은 진짜 걔는 인생에서 평생 동안 엄마한테 까요. 야, 내가 놀지 말라 했잖아. 나한테도 까요. 야, 놀지 말라 했잖아, 내가 어떻게 하냐고? 맥쿼리 유니버시티 그 라이브러리 가가지고 애들이 겁나 놀아요. 막 거기서 내가 심지어 어떤 경우는 술 마신 애들도 봤어. 어떻게 그런지 모르겠. 그러니까 왜냐면은 오버 18이잖아. 걔들은 술을 살 수가 있어. 사와가 테이크 해가지고 거기 맥쿼리 조용한 스팟이 있거든. 알아. 그러니까 세큐리티 맨날 돌아 거기. 근데 거기서 막 애들이 술 냄새가 나. 이러고 뭐 담배까지 내가 뭘 안 그럴게. 뭐 그럴 수 있어. 스트레스 받으니까 베이핑 그럴 수 있어. 뭐 나 그런 것까지 하나하나 캐치하고 싶지 않아. 근데 술은 좀 아니지. 왜냐면 술 마시면 기분이 좋거든. 기분이 좋으면 기분 좋은 상태로 공부하고 싶을까? 놀고 싶지. 그러니까 저 너한테만 얘기하는 거 아니야. 막 그렇게 막 죄책감 얼굴 하지 마. 괜찮아. 그냥 이제 스테이지에 따라서 내가 너희들한테 지금 이거 해야 돼 얘기를 해줄 텐데 그것만 해줘. 그러면은 어느 정도 아니면 좀 네가 또 하고 좀 부족한가 싶으면은 조금만 더 하면 돼. 그러니까 아까 말한 것처럼 한 스텝만 더 하면 되고 하나만 더 하면 돼. 생각보다 지금 10학년 애들 공부 많이 안 해. 네 친구들 보면은. 너희들 친구들 보면은 공부 그렇게 열심히 막 죽을 듯이 하는 애들 걔들은 이미 공부 끝난 애들이야. 계속 할 애야. 나는 majority를 얘기하는 거다. 한 95%는 공부 안 해요. 그러니까 나머지 5%만 해도 너희 벤6 나와 진짜로. 벤6가 뭐야? 95에서 8타 좋은 점 나올 수 있어. 그러니까 지금 공부하세요. 조금씩만 하세요. 한 스텝만 더 하세요. 뭐 지금까지 6시간 했으면 1시간만 더 하세요. 그런 식으로 생각하면 돼. Okay? So, we're going to go through some questions from your homework. Been a while. You're doing some stoichiometry questions. So what I'm going to do is I'm going to give you some, is that the question? Question 6? Yeah, must be. Yeah, okay. Oh, okay. All right. So it's been a while that you've done some stoichiometric questions. So I will provide you you look at the second page. There are 2 question 6s. I'll provide you a template for the stoichiometric questions as I did like so. More likely, whenever you need to deal with some chemical reactions, which called a stoichiometric question or finding number mole questions, you always need to start out with the balanced chemical equations, including the states. Okay, so state is something that's very important now, as I emphasized from year 11. If you got it wrong in the state in your balance equations, you most likely you get a no mark for that. Also, for the especially for the acid and base, about like a 90% chance you get the aqueous to the aqueous mix, solution to the solutions. Okay, there are some occasions that you're putting some solids, and in case you're putting the solid into the aqueous solutions, the question indicates that we have a solid ready. We solid put it into that. So don't miss that. Read the question very carefully. As I said, highlight it. You can bring your highlighter in, highlight it, and then don't get that wrong. All right, after that, you gotta find. Obviously, you can write, or you don't have to, but personally, I would rewrite and rearrange all the relevant information given, plus figure out any like a hidden information from the question. What I mean by rearrange is if you're given the unit of the milliliters, then you might need to convert it into the liter forms too. So unit conversions, that's what I mean by rearrange. And all the relevant information, like and this is kind of like preparation to get to move on to the next step. Figure out any hidden information too. Sometimes you need to figure out, the volume is not given, but from the mass of the water, probably you can just figure out that's going to be the same too. So that's something you have to think critically. So this is the step that you have to do before you move on to. Then you find the N, which is number of moles. More likely, you need to find the number of moles. There are a few methods to find the number of moles. That N can be found by mass over molar mass. That's for solids. Okay, when you're given solids. N can be found by CV. That's for solutions. When you're given a solution with a concentration volume, you're able to find that number of moles. We can also use PV equals to nRT. Okay, so N equals to PV on RT. Okay, that's for the gas state, for ideal gas flow. Or you can even use N equals to the molar volume times that divided by 2. So, okay, so that's V from the N times Vm. Yep, so hi, Orin. N equals to V over Vm. That's the gas state, that's what 2. Gas at 25 degrees Celsius or 0 degrees Celsius too. So 25 degrees Celsius, regardless of type of gas, the type of the molecules, it always have the molar volume of 24.79. It will be given on your formula sheet, by the way, so you don't have to memorize it, but if you can, like that'll be great. You can save your time. So, and this is a tool that you can think critically that, oh, we are given a gas, we're given a something, then you got to figure out how to find the number of moles. Okay? And some occasions that you need to identify the limiting reagent. Yes, you know why you deal with the limiting reagent, but when you're given, like this is a case like when you're given two given known moles in the reactant side, then most likely you need to find the limiting reagent of the reactions. If you're just saying, given the questions like, hey, we have excess amount of something. So in the combustion reaction, for example, we have some methane gas and an excess amount of the oxygen, then you don't need to worry about the limiting reagent because you have excess amount of oxygen that fully accomplished or fully reacting with the given methane gas. So in that case, you don't have to worry about the limiting reagents. But the questions like this or like some other question 7 I'm going to go through today, you might need to think about the limiting reagent, and this is something that's very, very, very important because by doing so you're able to, sometimes you need to get what excess reactant or like some amount of water, H2O, among H2O in acid and base reactions. This is something we commonly use. And depends on the question. Sometimes you're asked to find the products. Sometimes you find there's something pH or POH, something we went through and we're going to go through today. Okay. And up to here, and then you find solve the question, it's more likely. So this is the kind of basic template for the stoichiometry that we practice a lot in the module 2 in year 11, and don't miss that. You can skip the step 2, depends on what questions you have to, but I recommend you to do it because it's giving you the better ideas of the information you got, and so you're gonna say it will save your time actually. That whilst you're doing this step 4, you don't have to come back to some information, reread the questions. Don't waste your time because most likely those exam questions, calculation exam question, will be like 5 marks, 4 marks, maximum like a 5 or 6. You only have 7.5, so 8 minutes And this is like a time attack. You need to save your time if you can. Okay, and you must save your time in some cases too. So let's go through a few questions. Question 6, and let's do the question C from it. So again, we learned about some acid and base definitions from the Lavoisier, and Davy, Arrhenius, Bronsted-Lowry. We're accepting the Arrhenius on occasions too, but we commonly use the Bronsted-Lowry, that taking the acid as proton donor, base as proton acceptor. So I hope you remember that. I'm going to go through that a bit later. So let's start and let's follow the template that I provide you to solve question C there. So you're given combines 15 mils of the 0.35 molar of the sodium hydroxide in a beaker with a 1.4 grams of the solid hydrochloric acid. This is what I mean by you need to read the question very carefully. Even though it's given hydrochloric acid, but as it's given a solid, you need to write your balance equation as sodium hydroxide aqueous. It's reacting with hydrochloric acid solid, producing that sodium chloride aqueous, and leaving that water out. Okay, so make sure you're matching the state and balance. Yeah, this is the one-to-one to one-to-one balance. Pretty easy balancing. Then let's write it down all the relevant information you're given. So what we have given first is given that sodium hydroxide concentration is given as 0.35 mole per liter. That's firstly given. Second, the volume of sodium hydroxide is given as 15 milliliter. Now, that's what I mean by you need to notice that is milliliter forms converted into the liter. That is 0.015 liter. Okay, or you can just simply 15 times 10 to the power of minus 3, because a milli is always the meaning that 10 to the power minus 3. Now, micro is 10 to the power minus 6, and nano is 10 to the power minus 9. I hope you remember that. Also, we have mass of the hydrochloric acid that's given 1.4 grams. Step 2 done. Okay, after we've done that, you're going to find the N of the sodium hydroxide. As we're given solution with the volume and the concentration times CV, make sure you show the relevant formulas to find the number of moles. That is 0.35 times 0.015. Where's my calculator? 0.35 times 0.015. You get 0.00525 mole. Make sure you write the units as well too. So this is for you. I mean, this is not for the marker. That you know that as soon as you see like the units over there, oh, that's I've got the moles over here. Or just underline it so that you can use that, reuse the value again too. Now, we are also able to find the number of mole of the hydrochloric acid, but this time it's given the mass. So you can't use CV, because some people ask me like, oh, do we have 1.4 grams of hydrochloric acid? Is that means the volume is 1.4 liter? No. You have to think clearly that we only use that when you know that we're given the mass of the water and using the density of the water. So in this case here, we can find the N of the hydrochloric acid by M mass of a molar mass. That is 1.4 divided by hydrochloric acid 1.008 plus 35.45. Make sure you show all that relevant working out. Don't just use your calculator, put the get the molar mass value. That's required. Plus 35.45, 1.4 divided by that, you get 0.0384 mole. So once you notice that up to here, then you can compare those given amount of the reactants. Those are the reactants given. Then you just say, oh, it's 1-to-1 reaction ratio, which means 1 mole for 1 mole. But we only have 0.0525 moles of the sodium hydroxide compared to 0.0384. So this is obviously much bigger than the amount given for the sodium hydroxide. Does it make sense? Okay. That gives you then, oh, it's actually then solid, doesn't matter. This gives you this. We got to identify that sodium hydroxide is the limiting reagent. It's not the limiting reagent. Okay, due to the reaction ratio according to the reaction ratio, I should say, same thing. Okay, that means that hydrochloric acid is in excess. It will be left over. Okay, once you get it up to here, let's now solve the question. The question is asking you, hey, find the pH of the mixture, pH of the system. Then you'd be questioning like, okay, we have a sodium hydroxide, we have a hydrochloric acid. You're able to find, maybe you're able to find the pH and pOH of the individually, but it doesn't go in that way. Thinking about the meaning of the neutralizations, the acid and base neutralization, that we're mixing, well, we're reacting acid and base, therefore producing something in, this is called a neutralized. This is state of the neutralization. State of the neutralization. What does it mean by the neutralization? What neutralizes state? That means the pH of 7, that's a neutral. Or it can say, oh, that's basically producing the water. And this is why we're only taking the number mole of the water when we're taking the, finding the delta H neut, which is enthalpy of the neutralization last week. So you got to think in here. Yeah, okay, all that sodium hydroxide react with the hydrochloric acid get neutralized. But we all still have excess amount of hydrochloric acid. So isn't that the mixture is now contains some water or the salt water. We ignore the salt because salt doesn't do, sodium chloride doesn't do anything in this state here, plus that excess hydrochloric acid. Does it make sense to you here? We have excess hydrochloric acid left with the solid, with some water there. Then what is the reaction between hydrochloric acid and water? That's excess hydrochloric acid, the solid. Water is a liquid that we formed there. That water now starts to react with hydrochloric acid. What is the reaction? Proton donor, proton acceptor again. Forms the hydronium ion, aqueous, and leaving that to the chloride ions like this. In other words, the concentration of hydrochloric acid in excess, wouldn't that be same as amount of the hydronium ion formed? Again. Does it make sense? Okay. So don't forget about sodium hydroxide. They've been all reacted. We don't have any sodium hydroxide remained because that's also known as limiting reagent. So, which means that if we can find the amount of or the concentration of the hydrochloric acid in excess, you should be able to find that concentration of the hydronium ion. Then can we find the pH from it? You should be able to find the pH from it. So let's find that. The amount of the hydrochloric acid as excess is therefore can be found by N over V. Okay, you're given amount of the N is by N of the hydrochloric acid that you're given minus N of the sodium hydroxide to find that what? Amount of the excess hydrochloric acid left over. Does it make sense? Do you understand the point of why I'm minusing these two? Okay, because some portion of the hydrochloric acid we reacted with some portion of the sodium hydroxide. Now, a volume. You're given 15 milliliter, first of all. Okay, you add it up to 1.4 gram of the hydrochloric acid. So just using the density in this case, we need to make an assumption that, okay, assuming that it has the same density as the water, adding the 15 milliliter plus the 1.5 gram, if you're taking that as 1.5 milliliter, the total volume is therefore, would it be 15.5 milliliter in this case. This is an easy miss by students. They didn't really consider about converting the grams to the milliliters. I mean, think about it's a common sense, isn't it? Like that you're putting some salt into the water, obviously the volume's getting increased. You expect the volume's getting increased. Not as much as we put the same amount of water though, or the ice, okay, putting the ice cube into the water, increase the volume too. Does it make sense? So the total volume is now be 15.5 milliliter. In terms of the liter form, that'll be all point 0.0155. Yes. Is it 15? Oh, sorry. 1.6? 1.4. Okay. Ooh. So 15 milliliter plus 1.4 grams, 1.4. So converting that into the milliliter, just using the density of the water. So you don't have to write it down assumption here, or you can do. Gives you 16.4 milliliter, same as 0.0164 liter form then too. You should put that in here, 0.0164. Then you get, let's write it down. That we had 0.0384, then minus 0.0525 divided by 0.0164. Sorry. You get 2.02 mole per liter then. Okay, this is what? Same as concentration of the hydronium ion. Then pH, make sure you show the relevant working out. Minus log 10 of the hydronium ion concentration is log 10, log that. You get, 0.3. Okay, and given the suffix of 2, your correct suffix in the pH would be 0.31. That'd be 2 suffix then. 2 suffix, yes. So this is the final answer then. Remember that in the pH on anything with the log, we don't count the number like in the front of the dot as a suffix. This is on the suffix that you're going to count. So in this case, a 2 suffix, but that's similarly the reason. Okay, so this is how you need to deal with those stoichiometric questions again. Start with the balance equation, okay, and then relevant information. I'll just rearrange that. Find the number of moles. Limiting reagent. Finding limiting reagent, especially in acid and base reaction, is quite common. It's really common. So after that, identify which will give you excess, get the amount of the hydronium ion from it, and then you can find the rest here. Just don't forget that the volumes is getting increased as you're putting some solid into the certain volume of the solution there. Makes sense? Okay. So some of the questions are very similar. Actually, did you figure out the question you asked me yesterday? No? Okay. What was that? Question 10. Question 10. Was that question 10? I think it's a question 10. It is question 10. Okay, question 10. So another hydrochloric acid question with the lead, but this time lead hydroxide. Let's do this. Let me know if you have any questions from this homework. I have about 20, 30 minutes to go through that. And we're going to go through more acid and base questions today. Okay, question 10. Hydrochloric acid is combined with the lead hydroxide in water. Let's write it down, the balance equations. We just might assume that, make assumption that this might be the just solution to solution forms too. So HCl, aqueous, maybe 2. Terrible. Lead hydroxide, they didn't even tell like what the valence is. Assuming that that's a 2, lead 2 hydroxide, because that's the most common lead we can find. So lead 2 or H2, the aqueous like this too, forming that lead chloride, most likely aqueous, and forming the 2 amount of the water. Yep, that's A. B. A student uses 250 mils of the 0.99 mole of the hydrochloric acid and 0.33 moles of the lead hydroxide solution. What is the final volume of the water which is produced in the reaction? Okay, tricky, because you will think, okay, they are mixed together. They're mixed together, so they'll increase the volume. Wouldn't that be same as the volume of the water? But remember that we may have some excess. We may also have some lead chloride left in there. So it means that it's not a pure water. The question is asking you, hey, find the volume of the pure water. So to find the pure volume of the water, you may need to find the mass of the water. And to get the mass of the water, you may need to find the number of moles from it. So how do we do it? Let's write it down, all the relevant information that we have. We've given hydrochloric acid has a concentration of the 0.98 mole per liter. Volume of the hydrochloric acid, that's given as 250 milliliter. Let's convert that into liter form, 0.250 liter then. 0.250 there. Okay. You're also given N of the lead hydroxide is given as 0.33 mole. So we don't have to worry about the number of mole of that. So from here, N of the hydrochloric acid can be found by CV, and that's 0.98 times 0.250. Actually, what you get? 0.245 mole. Okay, compare the value. The reaction ratio between hydrochloric acid to lead hydroxide is 2 to 1. For 1 lead hydroxide, it needs 2. Okay, everyone good up to this point? Then we have 0.33 moles of the lead hydroxide. So theoretically, as we have a 0.33, we need to have 0.66 of the hydrochloric acid. 1 to 2, 0.33 to 0.66 then, okay? But we only have 0.245. Does it make sense? This is how you need to think about the limiting reagent. We can write it down full working out, or just saying hydrochloric acid is the limiting reagent according to the reaction ratio. Does it make sense? Okay, then you gotta consider about these values here. This is the only mole that involved in the chemical reaction that it will react, fully reacting, fully consumed. Okay, and the number of mole N of the H2O is then same as number of the hydrochloric acid that you have. That's what, given that 0.245 mole. Good up to this point here? Okay, it's very simple from here. How do you find the M of the H2O from N? M equals to N times the molar mass. That is 0.245 times that, 2 times 1.008 plus 16. It will give you 4.41392 gram. What is the density? Using the density of the water, which is 1 gram per milliliter. The volume of the H2O is then 4.41392 milliliter. Yeah, as we found the grams. This is in the liter form, that's 0.0044. And how many sig figs are we given? 2. So 0.044 liter into sig fig. This is the final answer then. Again, there's something we learned in module 2. This is actually what I can give in the module year 11 students as well too, because that's exactly the same, the working out that we're using. Okay. Okay, Joanna, do you have any questions from the homework? Yeah. No? Okay. Judy, do you have any questions from the homework? The question you couldn't do, you didn't know how to do it? No? Orin?
Question 7B.
7B.
It's just like a word.
B? This one?
It's like copper, yeah.
Okay.
The green one.
Copper is green, white copper surface blue. How can you determine whether the reaction occurs? Oh, spontaneously. Okay, you started with the copper carbonate that is green. Okay, so we let's have it right here. sulfuric acid H2SO4 aqueous plus copper CuCO3. That'll more likely, I don't know, maybe aqueous. This is aqueous actually, carbonate. Producing that CuSO4 aqueous plus 2H2O plus CO2. Oh, sorry, just one H2O. Important thing is, okay, I want you to think about, imagine about, before you perform the experiment, you prepare, you're doing some preparation. So your prep work is, you prepare some copper carbonate that is green. Okay, that means you have now fully like a green solutions, and sulfuric acid is known to be colorless. So you're putting some colorless solution into the green solutions. As you do so, what happen is the color change to the blue. It's not going to permanent perfect blue. So you just start to see mix of the blue and the green. Okay, and then it'll be like greenish blue, bluish green, and gradually changing the colors as you proceed, and you're adding some sulfuric acid in it. Now, whether the reaction occurs spontaneously means, how do you know it happens spontaneously? Like, what does it means? Think about the meaning of spontaneity. Do we need to do anything to make a color change? It means that you will see the color change quite instantaneously. As soon as you put in the sulfuric acid to that copper carbonate, then you start to see the color change from green to greenish blue or bluish green. That's the evidence of that. Oh, it doesn't need it doesn't need any help. It's just like a rolling a ball in the downhills. You start it, you just start rolling down. So chemical reaction occurs spontaneously and instantaneously in that reason. Make sense?
Yeah.
Okay. Okay, and the rest is just doing some questions about it. Anything else?
No.
Nope. Okay. So let's do more some questions related to the acid and base. I will collect that homework at the end of the class today, so it's getting marked, and you probably get the actual marks for those, because it has allocated marks in the each questions. I'll ask my markers to do it. All right, workbook please. Again, chapter 2, page 73. Let's do a little more about the pH and pOH. Okay, let's revise that where we're up to. First, we learned about acid and base again. So please don't forget that acid is the H plus donor. Base is H plus acceptor, according to Florensted-Lowry definition there. Okay, I just write that as a side note. We're going to keep using that. So when we're diluting some solution then, and we learned that pH is from that, again, water and water, it's quickly revising, water is known as what? According to Bronsted-Lowry's definition, this is known as amphiprotic. It can be acid, it can be a base, it can be protein donor, protein acceptor. So it will have something like, when the two water molecules combine or reacting, it's a big reaction, so producing the hydronium ion, same time producing the hydroxide ion like that too. And we learned that at 25 degrees Celsius, okay, the concentration of the hydronium ion the same as the hydroxide ion, that's 10 to the power minus 7. This is how we get the pH, which is mass log 10 of the hydronium ion, same as hydroxide ion, okay, by 7 at room temperature. pOH minus log 10 of the hydroxide ion, that is 7SO2. So adding these two up, so pH plus pOH gives you 14 in the sum. This is where we're up to. Okay, so briefly I can explain revising that. Now, when we're diluting something, so dilution, how does it affect the concentration? It's a really simple question, by the way. We're diluting something, you're diluting the concentration. So in terms of quantitative, in terms of numbers, it will decrease the concentration. Yep, it's not that complicated. As referring to C equals to N over V, when the V is increased, and C must be decreased because they are inversely proportional. So in some cases there, this is actually how we making the primary and secondary standard solution there. You prepare something, you put it into the volumetric flask, and I hope you remember like making the sodium carbonate solutions to volumetric flask. You prepare something, and you basically make a concentrated standard solutions. So you draw out something, and you mix with the water again to make a diluted solution. So for this dilution process, you need to know how to calculate it. Calculation is pretty easy, to be honest. You also need to know the method of diluting a solution from the standard solutions. This is related to the quantitative analysis. So I'm doing some practical works too, because sometimes you'll be asked to like, oh, hey, dilute that first. Okay, so it means that you should be able to calculate how much volume is required to get this certain amount of the concentration as well. But in the case of that, let's go through the example. But for dilution, okay, calculate the molar concentration of the hydrochloric acid when 10 ml of water is added to the 5 ml of the 1.2 mol liter of the hydrochloric acid. So easy process. The C1 V1 equals C2 V2. You can just use that. One thing for the process of the C1 V1, it's actually conversion of unit is not necessary. Okay, so if you're given milliliters, you can still follow milliliters because they are talking about the ratios in this case. So it's kind of the method that you can save your time. So what we have given, 10 ml of the water is added to the 5 ml of the 1.2 molar. So given that 1.2 as a C1, okay, and we have a 5 milliliters, as I said, I'm not gonna convert the unit to the liters too, because you get the same result anyways. C2 is unknown. Now, the problem is you need to read the question very carefully. The question is not saying the total volume of 10 ml. Okay, it says 10 ml of the water is added. Okay, that's kind of a little trick that you have to figure out. So 10 ml added to where? The 5 ml. So total volume is now 15, not the 10. Does it make sense? A bit of simple. So 15 is a thing. The C2 simply be 1.2 times 5, which is 6 divided by 15. 6 divided by 15. What do you get? 0.4 mol per liter. That's it. Again, conversion to unit is not necessary, so you can. Even if you do it, you get the same result though. Okay, except the concentration. Concentration is something that's very different. Next one, calculate the molar concentration of nitric acid. When 80 ml of the water is added to the 20 ml of the 5 mol of the nitric acid. Okay, so concentration of nitric acid, new concentration, C2, can be found by, you can do this, C1 V1 over V2. You can also do that. C1 that we have a 5, initial volume of 20. Now, remember that 80 ml added on to 20 ml. That is 100. Oh, pretty easy. So 100 divided by 100 gives you 1.0 mol per liter straight away. Okay, see how much water must be added to 30 ml of the 2.5 molar hydrochloric acid to dilute the solution to 1 mol per liter. So the question is now asking to find the volume. So the volume V2 can be found by C1 V1 over C2 from the formula there. The C1 that we are given is initially 2.5 times that 30 divided by new concentration of 1. That gives you what? 7.5. 7.5 milliliter. So that's a final volume. And initially, how much we had? 30 mils? Oh, hang on. Oh, no, 75. Not 7.5. 75 milliliter. Like that, okay? So that means from the 30 mils to make it 75, 45 milliliter is added. Too easy, okay? Then why am I talking about these dilution too? Because you're going to find this question like a question D, find the pH of it by using the same method. So let's do D. 5 mils of the 0.1 molar nitric acid is diluted to the 100 mil. Diluted to 100 mil. Remember that, the final volume 100 mils. Calculate the pH of the diluted solution then. Okay, let's do it. 5 mils. Concentration of the nitric acid, new concentration is found by C1 V over V2. The new first concentration is 0.01 times that. The 5 mils, just leave the 5, doesn't matter. And then we got the 100 mils for the new volume. Gives you 0.05 divided by 100. That's giving you some 10 to the power minus 5. Let's check it again. Yep, minus 4. 5.00 times 10 to the minus 1, 2, 3, 4, minus 4. Mole per liter like this. Okay, means that the concentration of hydronium ion, we make assumption that the same as HNO3. This is therefore pH, which is minus log 10 of the hydronium ion. I know you can't be bothered to show that every single time, but make sure you do it for separate questions. And then after that, you put that into log, you get 3.3. Sig figs of, how many sig figs are we given? 2? The minimum 2 sig figs. So the correct answer would be 3.30. That's a 2 sig figs. Don't question that. This is the first number is not counted as a sig figs, so only the decimals. That's how you do the first one. Okay. E, 10 mils of the 0.1 molar sodium hydroxide is added to. Okay. Calculate the pH and pOH of the diluted solution too. So again, concentration of sodium hydroxide can be found by C1 V1 over V2. Make sure you write that. We get the 0.1 times that 10 mils divided by V2, the 100. So that's giving you, cancel that. That's giving you 0.01 mole per liter. Then from here, okay, sodium hydroxide, it's impossible to find the pH directly from the sodium hydroxide because it's a base. So what we have to do, we have to concern that sodium hydroxide will release the hydroxide ion. That's according to the Arrhenius definitions then. pOH instead can be found. And the question also asks for the pOH value too. So that is log of the 0.01, then you get 2. But when the pOH is 2, then pH, which is 14 minus pOH, that would be 12 then. This is the final answer. Okay, let's fix that into a sig figs as well. I forgot to fix sig figs. You're given 3, 1, and 4 sig figs. Okay, so you have to follow the lowest sig fig value, which is 1 in this case. 2 is not a sig figs, so you must write in 2.0 and 12.0 for the 1 sig figs. Okay. F is kind of a similar question. Let's skip that question for now because I'm going to spend more time to something else. But does it make sense how to find the the pH, pOH using dilution process? So pretty easy. Please read the question very carefully and highlight it because sometimes the question is giving you, we edit or we made the full concentrations, okay? All right, next page, page 77. This chapter 2.3, the strength of the acid and base, is something that known as I would take that as the most important concept of the year 12 acid and base. Yes, you will see, you will get at least 2 to 3 questions about the strong acid and strong bases too. So when we're saying the strength, so let's compare that in here. So probably we did that in year 10 a little bit, but today we're gonna more in doing more depth. Ask you very simple questions, guys. Okay, if I ask you, hey, what's the difference between strength versus concentration of something? So I want you to think about literal meaning of the strength or literal meaning of the concentration. When I'm describing something is, something's really strong. Okay, I'm not talking about its quantity, the amount it has. It doesn't really matter how many we have. It's more like individual characteristics that, oh, each of those are really strong. So like, oh, all the 4 of you are really strong. But when I'm talking about concentration, as we discussed in the dilution process too, I'm more talking about when I say, oh, something's really concentrated. It doesn't have to be strong. Does it make sense? Okay. Does it like kind of make clear sense? This is something that I'm comparing these two. So when I say strength, I'm talking about its quality of the individual. That how strong it is. It's really strong. Each one is really strong. 10 is really strong. In that case, we don't really count for any quantitative. But concentration is something that we're dealing with, the quantity of the groups. So we use the same terminology in chemistry, especially in acid and base. We sometimes have strong and the weak acid and base. But let's talk about strong acid first of all, strong acid or base, and talk about it a week bit later. Strong acid or the base. And we can also have concentrated acid and the base. Okay, actually, when I say strong acid to the concentrated acid too, can you like figure out the difference between strong acid to the concentrated acid? Can concentrated acid be strong all the time? I'm like saying we have a group, 100 people there. Can all 100 be like strong? It's just kind of a separate question. I'm asking you some stupid question to be honest, because this is kind of two different terms, two different characteristics. One is talking about how many we have. So when I say concentrated acid and base, I'm actually asking you the quantitative value of, hey, we have a 2.0 mole per liter. This is quite concentrated. Or say 100 mole. We don't really get that, but this is super concentrated solution then. Okay, but it does not determine the strength of the acid or base because, as I said, individual might be different too. So when we define the strong acid, when we just need to define it, as we define the strength is defined by how much work it can do, how much weight he can lift. Similar things happen in the acid too, and using the definition of the acid and base and Bernstein Lowry, that acid is known to be hydrogen donor, base is known to be hydrogen acceptor. So when we're saying they are strong acid, that means that this will be 100% dissociation. I'll probably ask you to remember the term, or the ionization of, so in other words, for the acid, 100% hydrogen plus donor. For the base, it would be 100% hydrogen ion acceptor. Important thing is, it's not the 99%, it's not the 90%, it must be the 100%. This is the standard to be a strong acid. Okay, and this is the reason why, when you're writing your reaction, for example, some strong acid, HA, the strong acid, plus H2O, we show that in a single arrow. Why? It's 100%. They don't come back, and they produce the hydronium ion, plus A minus, like this. So single arrow in the chemical reaction is representing that this is a strong acid. Does it make sense? But does it make a logically sense that, yeah, this is strong, means individually they are dissociating, they are releasing their ions 100%. It doesn't matter like how much we have. We can have so in the case, we can also have the diluted strong acid. Okay? That means we can have a concentrated weak acid too, later on too. All right? So, example of strong acid, this is something that I ask you to memorize as well too. Strong acid, we have hydrochloric acid, sulfuric acid, nitric acid. Those three are the strong acid that we use in school laboratory. Only three for now. Phosphoric acid might be a little strong too. Okay, these are typical. Now, weak acid. Think about the meaning of the weak then acid here. Then we have weak acid and base, compared to the diluted, the acid and base. Again, just as we discussed about concentrated here, diluted means that it's related to the quantity, how many we have in that volume. So when you say, oh, 10 to the power minus 7 mole per liter, I mean, this is quite diluted. Okay, or 10 to the power minus 10 or 100, even that, it's just quite exaggerating. We don't really get that. It's pretty much nothing. You didn't see, like, if we say, oh, we have a hydrochloric acid concentration 10 to the power minus 10, 100, that's like, okay, that's basically water. Does it make sense? Okay. Now, weak. To define the weak means it's something that you can't do work. I mean, not individually. So it's not means it's just simply it's not 100% dissociating, or the ionizing the water. Important thing is anything below the 100% would be considered to be weak. Yeah, it's quite strict, 100%. Okay, so means that acid would not be it's not 100% hydrogen ion donor, and base would be it's not 100% hydrogen acceptor too. So if in the case of we have weak acid, if we have weak acid dissociating with the water, we show that in double arrows. That's producing the same product, hydronium ion, and it's a leftover metal. So this is the key, the double arrows or single arrow, to determine that whether the acid is strong or the weak in chemical reactions, which is kind of makes sense because it's weak, which means that the product part we can go back to the reactants too. And this is one of the reasons why they can't be 100% of dissociation, because they are obviously coming back to the initial state of the reactant. Okay, so make sure you put the right arrows for the strong, single, weak, doubles. Typical example, the weak acids, we have ethanoic or acetic acid, we have vinegar, in other words, carbonic acid, something acid you have in your soda or soft drink. Phosphoric acid is known to be a weak acid in this case. Strong bases, we have a typical example of the hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, known to be strong, so you must follow the one single arrow. Weak bases, ammonia is known to be the typical weak base we use in chemistry. Pyridine, that's some organic base. Adine, so I'm going to come back to this, amine, adide too. Dimethyl amine is also known as the weak base. We're going to talk more about those organic bases in Module 7 and Module 8 later on too. You don't really need to worry about how they look like, the shape like. You're going to learn everything. Does it make sense? Okay. So let's have a look at some, this is a kind of chart, strong acid and weak acid given. I love that. Strong acids are molecules that completely dissociate into their ions when it's in the water. pH of strong acids is very low, therefore too. Yes, acid dissociation constant is higher, and release of the hydrogen ion to the solution. That weak acid would be quite opposite. But ignore the second section over here. Okay, this is kind of right and the wrong in the same time. I'll show you what that means by doing this. Okay, Joanne, what is the pH? Why do we use the pH for? Acid and base. Okay, so when we're going into like some mathematical expression of that, what's making the pH? Isn't the pH is simply related to the concentration of the hydronium ion. So pH is not measuring. It's not really clearly measuring the strength. Why? As pH is found by minus log 10 of the hydronium ion all the time, I should say. It does sometimes, but not all the times. I tell you that when we are using the pH as like measuring the strength, when we're not. Okay, assume that we have the situation over here. I have super concentrated. Just have a look at the board for now. Concentrated. These exam questions we love to put in. Concentrated weak acid. Okay, versus that diluted strong acid. So giving an example, acetic acid, CH3, COOH, with the water, producing hydronium ion and acetate. Forget about the state for now. Okay, as I said, I show you that this is like a diluted. The weak acid forms too. Strong acid, hydrochloric acid. Let's just show you that this goes to release that straight away. Or you can just show with the water, hydronium ion, like this. Doesn't matter for this now. Okay. Assume that concentrated acetic acid, we have 10 mole per liter of the acetic acid, which is really, if you ever heard it's a concentrated vinegar. Has anyone seen that before? Okay, it's a double strength vinegar or something like that. It's concentrated. The other strong acid, let's say we have 0.001 mole per liter of the hydrochloric acid then. Everyone got up to this point here? Now, when we're counting the pH, remember that we're only concerned about amount of the hydronium ion. Okay, it's not about the concentration, the actual acid that you're given. But we can only do that. As we know, the strong acid is something that always 100% dissociating. Means that if we have 0.10 mole of the hydrochloric acid, 100%, all of those get dissociating into 0.001 mole per liter of the hydronium ion, isn't it? Then pH of is what? Log 0.001, you get 3. pH of the 3. So can we consider that pH 3 is quite strong? Not okay. Like depends. It's reasonably, but it's something that lower than what we expected. Because when we said strong, it may be like reaching to like somewhere like pH 1, even lower than pH 1 sometimes too. But it's only pH 3. It's kind of okay. It's not too bad for the strong acid side. What about weak acid? This one here. We have 10 moles for the acetic acid there too. So when we put it into the pH meter, we found out the pH is also be 3. That's sweet. So we can have a situation where exact same pH, but it doesn't really relate it to its strength. It's more related to their concentration. Now, why would it have only 3, even though the acid concentration 10 mole per liter? As I said, not all the 10 moles will be dissociating. Okay? Think about it here. We found that it's only 0.001 mole, same amount of hydronium ion is only formed. Out of how many? Out of 100, out of 10, we only get this. Is that like, let's do a simple calculation. In percentage-wise, that's less than like 1%. Does it make sense? Okay, so only so when I'm talking about weak acids, we're generally talking about their percentage-wise, they are really lower than 1%. Only 1% or less than 1% of the acid will be dissociating. Does it make sense to all? Okay, so this is why I kind of ask you to skip that. It's not really, depends. If you have a high concentration, we can still have the relatively high pH value too. This was a HSC question in many years. Not only one, out of 10, in 10 years, we had 2 or 3 HSC questions related to that. Or some kind of similar fashion. They're asking you, hey, we have a concentrated, or the question was like this. We have a same pH of the 2 acids, and one is acetic acid, one is the hydrochloric acid. Why would they have the same pH, even though they have the same different concentration? So you should be able to write the full answer. That was worth like 4 marks, 3 to 4. Okay, and you will see what I mean when you get to some HSC question later on. Any questions up to this point? Here. Now, this is my this is not a real, by the way. I just made it up, to be honest, okay? But this is real. This has always been happening for the strong acid. Now let's go back to the weak acid part given over here, this side over here. Yes, I gave you the percentage about less than 1.1%, but I want to know the real a percentage. I want to know how many of those weak acids will be dissociating. Okay, and to get that, we need to use something known as, it's been a while, equilibrium constant. We have to use this to determine. Okay, let's bring out the equilibrium constant too. Like this time, let's use acetic acid. Let's rewrite that. CH3, COOH, aqueous reacting with the water, producing that hydronium ion, aqueous plus that to the acetate. Given here like that. Okay. Now, this is in dynamic equilibrium, which means every single time, like every single moment, these reactants will be dissociating, reacting together, producing the product, coming back to the reactants too, which means we are able to find the K value. Remember, the K is bounded by product divided by the reactant. So in this case, it would be hydronium ion times that acetate that you have divided by acetic acid at the equilibrium. Okay. Now, one question. All right, do you expect the K value be 1? 1 as in like, do we have the same concentration of these product to that? No. Do you think that this K value will be, think about the property of the weak acid too, and using some of the examples that are given here, do you expect this K value to be less than 1? Or small, even like further smaller than 1?
Yeah.
Yeah. Why is that?
Because it like only dissociates like a bit.
A bit.
Yeah.
There we go. It means dissociating. Think about the meaning of dissociating all the times too. Okay, means that it only produced a small amount of the products. It's a really small amount. So rest of those will be left over as the acetic acid too. So we are massive. The acetic acid reactant, really small portion of the product. So this will be actually less than 10 to the power of something, -4, even further. We kind of learned that in KSP, that when the K value, when the K value is significantly small, means that it's representing that it's almost like there's nothing much to produce to. Okay, so that's how we determine that. So in case of that, don't worry about the 10 to the power -4 for now. Okay, in case we're dealing with the K for acid, we put that as Ka. That acid, the A for the acid, means we can have a Kb as well for the base. This is known as the acid constant there. Instead of saying equilibrium constant of the acid reaction, it's too long. I just simply say acid constant because it will have the Ka value. So Ka is more likely a good standard, more tools and the greater tools than pH to determine the strength, which means, remember this, greater the Ka, the lower Ka. Okay, having the greater Ka, considering the meaning of the K, that we have a greater K means we have a greater amount of the products produced, which means it's a fully ionizing, more likely be a stronger acid. The acid. So it's very simple. Oh, we have a greater acid constant. That's representing this means the acids must be more strong, more powerful. Lower Ka, in other words, means the weaker acid. Okay, but just like the pH given over here, we don't really like to deal with some big number like 10 to the power of the 4, really complicated numbers. I want you to think about the meaning of the reason why we're using the pH, which is -log. We love to use something known as index number. Okay, giving something as the whole number, like a pH 2, it's kind of giving, okay, that's really kind of concentrated. pH 7, pH 8. So we also love to use something known as pKa. Just P stands for, remember the P stands for anytime -log 10 of something. Okay, as we learned, pH was -log 10 of the hydrogen ion. Okay, when we say pKa, this would be simply minus log 10 of the Ka value you would have. Then think about the relationship there. As we learned for the pH, the greater the concentrated hydrogen ion represented as smaller pH, wasn't it? 10 to the power minus 7, 10 to the power like greater pH, or like greater concentration of the hydrogen ion representing the smaller pH value. Which means if we have a greater Ka, there's a bit of a mathematical approach too. I mean, it shows that smaller pKa value. Lower K means the greater pKa value to 2. In other words, when you're given the pKa values, which is the index values, you're able to determine that from the small pKa, it will determine the stronger acid. Greater pKa determine the weaker acid. So pKa is a term that we use to determine the strength of the acid, and acid in this case. We can also have pKb, that is what? For the strength of the base in this case. So remember that the pH is not always the measurements or the tools that we can determine the strength of the acid nor the base. It's actually the pKa, the one that measuring to. Okay, do we have that in here? Remember that. So I'm just covering the page 84 now, the pKa, KEQ values. So let's have a look at page 84, please. Skip some of the questions. So let's have a look at that in here. Ethanoic acid, known as what? The weak acid too. It has Ka value of the 1.7 times 10 to the power minus 4, minus 5. That's pretty small, isn't it? And consider the meaning of that 10 to the power minus 5. We don't have much products produced. Still be remaining lots of the reactants. Then if you find the pKa, it shows that 4.76. Okay, so we kind of consider that to be that's the weak acid. For the citric acid, the sour taste, it's also be 10 to the power minus 4. pKa value of 3.14. Phosphoric acid, 2.15. So you'd be saying, oh, this is quite relatively low. I mean, compared to pH. We learned that pH is like a 1 is the really concentrated. But have a look at the pKa of the strong acid. It's going into the even further minus. So we are using some negative the numbers to determine that the pKa. So that this means, oh, we have a really small pKa value. That's a negative even. Means that that's a super strong acid. Okay, so all that nitric acid, hydrochloric acid, sulfuric acid, they have high Ka values. Can you say that 20? We have a Ka value 20 means what? All that nitric acid will get dissociated. Even if you have 10 to the power 7, that's huge. We don't have anything like any reactants left over then. So that's how we determine the strength of the acid then. You do not need to remember any of those Ka, pKa values. We use quite a lot of the ethanoic acids, by the way, in the calculation later on too, but it's more likely those values will be given. So don't get stressed about memorizing those two. I won't ask you to memorize. I won't ask you to memorize something that you don't have to. Don't worry about this. But what you need to understand is, I'll just explain the really important contents about strength, and the concentration. Okay, so make sure you're able to figure out to differentiate them. We can have a situation where we are concentrated weak acid. We can also have a situation where diluted strong acid too. So how do we use those Ka values and pKa? This is how we use it. pKb, okay, forgot to mention that. Kb is in that case of they were producing OH minus there like this too. We don't really use the Kb a lot too, but nowadays in HSC they like to put the Kbs in the calculations quite a lot. So it's good to know how to find the Kb. Exact same as to find the Ka values. You see that Kb, smaller the Kb, the greater the pKb values. They're all representing what? Weak bases in this case. Okay. All right. So how do we use that? The reason why we learned that is we're going to use that to find something. So 2.13, after we do this question, we're going to have a break. let's do this. The Ka for ethanoic acid is 1.7 times 10 to the power minus 5. For a 0.5 mole ethanoic acid solutions, first, calculate the pKa, 2, calculate the pH, and then calculate the percentage dissociation. We're going to talk about this as well too, okay? Let's do it. Always start with the balanced chemical equations of the, so in this case, ethanoic acid, CH3, COOH, aqueous, reacting with the water, H2O liquid. Make sure you show the double arrows to show that it's a weak acid, producing the acetate and the hydronium ion. Like this, okay? So Ka would be, let's write the expression, the Ka, or Ka expression would be concentration of the acetate times that hydronium ion divided by acetic acid at the equilibrium, by the way. That's given as 1.7 times 10 to the power minus 5. That's given. Okay, now 10 to the power minus 5, is that the really big or small? This is relatively or significantly small value. Okay, consider that. We've got to use that value, the small value as well too, in the calculation. So let's do A. Let's find the pKa. How to do it is simply minus log 10 of the Ka value. Okay, so I put that into the calculator. You'd get log 1.7 times 10 to the power minus 5, and then pKa, log of that. You get 4. So given the sig fix of the 2, your value must be 4.77 in 2 sig fix. Again, I don't only count the decimal as my sig fix values. So it's a positive, it's relatively high. Yeah, okay, I would consider that. This is actually quite weak. Any questions up to this point? Too easy. Don't get confused. Higher the pKa, weaker the acid. Higher the Ka means that higher the Ka means that it's a strong acid. You will get confused at a certain point too. So try to memorize, try to differentiate that, or think about the relation to the pH as well too. All right, let's do the pH calculation from it. To find the pH, think about what we need to find the pH. pH requires to know that concentration of the hydronium ion only. So, which means if you are able to find the this concentration, we are able to find the pH too. So how do we do it? Remember that initially you're given that 0.50. So what I'm going to do is I'm going to reconstruct rewrite that H2O liquid. I can actually skip that, but aqueous like this, and I'm going to put that into something we've done in module 5, the ice table. Okay, so initially you're given 0.50 mole per liter of the acetic acid. What we do, ignore water. Water is not important because we don't really count for the Ka calculation expressions. Initially, you're given 0 and 0 for those. Okay, now consider here, change would be what? It would be minus x, plus x, and plus x. As a result of that, you get the x, and what do you get? 0.5 minus x. Okay, this is the point. We discussed that. We just kind of clarified that this is a relatively small Ka value. Think about the meaning of that. It means that we don't get much of the products remained. All of those will be slightly changed. There's slight change. So can we consider that x is compared to the 0.05 is relatively significantly small. So therefore, this is same as 0.5 as. You can also do that. I mean, you can solve the quadratic if you like to. In some cases, you need to solve the quadratic. In a case that with the 10 to the this value, Ka value is relatively bigger. Saying if that value is like 10 to the power minus 2, I would not recommend to skip that sometimes, or 10. You need to consider solving the quadratic in that case. That would be really tricky, but just use the quadratic formula. Okay, once you get it there here, K expression, this is the same as what? The same as x squared on 0.5. then you're almost done. X can be found by 1.7 times 10 to the power minus 5 times 0.5 square root of that. You get 1.7 times 10 to the power minus 5. That times 0.5 and square root of those. You get 0.002914. Try to show like some exact values because we are not looking for the final answer yet. This is the same as what? The same as hydrogen ion at the equilibrium. We're almost done. pH, show that minus log 10 of the hydrogen ion. Then put that in your calculator. You're going to get 2. Check the sigfigs. We have a 2 sigfigs given. That means your answer must be in 2 sigfigs too, which is 2.54 in 2 sigfig. This is the final answer to find in pH then. Is everyone comfortable using the ICE table? Did we practice that a lot in module 5? I asked you, I made you to do it. I gave you so many questions about KSP, KEQ calculations, and I'll probably say like, oh, guys, you want to use that again in module 6. This is how we use it, using the pKa or Ka values. Then C. Let's find the percentage dissociation. So the meaning of the percentage dissociation means that we want to know from how many of those acids get dissociated to the or involved in the chemical reaction in what percentage. Does it make sense? So to find the percent dissociations, it's actually given on the top. Do we? Here. Page 86 shows you that. Percentage dissociation can be found by I'll rewrite it here. Percentage dissociation can be found by concentration of the A minus. Now, A minus means that something that's not the hydrogen ion, something that we have in here, okay? Divided by concentration of the HA, the initial, and times that 100%. So that's more likely at the equilibrium, the concentration at the equilibrium of the, but we know that there's not much change for the HA. Or like the initial, I should say, initial concentration of the acid that you're given. We don't know how many of those got dissociated. And so in the case of that, we have concentration of the A minus, which is acetate, is same as this one, 0.002914 mole per liter. That's what we found from the X, which is the same as the concentration acetate. Okay, that divided by HA, that's what? 0.50 times 100%. So that divided by 0.5 times 100, times 100. Ooh, you get 0.58%. So as I said, less than 1%. Like if you have 10,000, if you have 10,058, will be that's a kind of nothing, because it's like, okay, oh, that's like nothing. Out of 1,000, maybe, I don't know, maybe 5. That's pretty much small. Okay, this is how we can find the percentage dissociation of the weak acid. Okay, strong acid, don't worry about it. It's 100%. That's what I'm about. Strong acid percent dissociation would be just simply 100%, because we know amount of the what we have is same as the what we used to have. It's 100% matching them. Does it make sense? Okay, this is an introduction of the calculation involving the acid and base in year 12. But I would take this as a basic, as a kind of basic and fundamental of the SM calculations, acid and base. But the applications, or there's some tricky questions always going to coming from here. It won't be that hard once you understand these points here. And in fact, you get lots of those basic questions in your HEC and sometimes in the trials too. So what we're going to do is we're going to practice more of those questions, and next week we're going to have a topic test related to this. It's been a while. Okay, topic test about all that, where we're up to. So basically, we finished the calculations. Once you feel more confident with dealing with those, Ka, pKa, pH finding, okay, we're going to move on to the quantitative analysis, that is titrations. So we're going to perform the prac, and in that case, we're going to. This is why you need to use, because sometimes they're asking you to find the pH value of it. Without understanding the pH calculations, there's no point of doing the prac. Any questions? No? Okay, let's go for a break. Let's try the full questions in class exercise 2.13 and page 88, and exercise 9 and page 95, and 13 and 19 onwards. Please give you about 15 minutes. just think the question full. Give you about 10 more minutes. Okay. Orin, been marked. Judy, Ashley, and Rachel. Module 5, the retest result as well too. Yep, Orin. Okay. Joanne. I actually have more for you, Jordan, than here. More. Stephanie and Joanne. That was test. Steph and Ashley. Okay, use that here. Okay.
And these are physics. I couldn't give you. Forgot to give you. Give you 3 more minutes. All right, let's start with okay, 2.13. Let's do it. Ka for hypochlorous acid is given as 3 times 10 to the power minus 8. For A, 0.1 mole liter of the hypochloric acid. Let's do that. So as the Ka is given as 3.0 times 10 to the power minus 8. For A, pKa, which is bounded by minus log 10 of the Ka value. That's log 3 times 10 to the power minus 8. You'd get 7.5. Given the suffix of 2, 5, 2 is the right answer. Okay, that's a 2 suffix. Make sure you're matching that suffix you're given. B, calculate the pH. Starting with the balance equation, HOCl, aqueous hypochlorous acid, reacting with the water, liquid, producing that hydronium ion, aqueous, and leaving that chlorate, aqueous. Put that into the ice table that you're ignoring the water at all too. Initially, you're given 0.1 molar of the hypochlorous acid, 0 and 0, so it'd be minus x plus x plus x for the changes, 0.1 minus x and x. But as this is, x is significantly, smaller, or 0.1 is significantly greater than the x, this is almost like 0.1 then. Okay. All right, after that, the Ka expression is bounded by hydronium ion times that chlorate divided by hypochlorate, like this. This is the same as x squared on 0.1, which is given as 3.0 times 10 to the power minus 8. Any questions up to here? Then x would it be 3 times 10 to the power of the minus 8 times 0.1 square root of that. You get 5.477 times 10 to the power minus 5 mole per liter. This is the same as hydronium ion. Let's write this one too. The same as the chlorate ions too. Yep, just in case. So pH, which is bounded by minus log 10 of the hydronium ion, that would be, put that into the log, you're going to get 4.26 in 2 suffix again. Yep. Oh, yes, but for the log index values, we only count the decimal as a suffix. Yeah. Okay. Same in here. pKa, 2 suffix. It's not 2 decimal, 2 suffix. So make sure you're matching that. Well, markers, obviously, we know that. That's a suffix, so you can get marks deducted. After you did all the hard work because of the suffix. Only for log. Only for pKa, pH, pKb, pOH. Only follows that. Only for log. Only for log. All right, percentage associations. Percentage can be found from that concentration of the A minus on a HA. Make sure that's the initial concentration of the acid you given, amount of the acid products you got left over times the 100%. For this case, in the weak acid, it would be 5.477 times 10 to the power minus 5 divided by 0.1 times 100%. So that's basically, even smaller, 0.055% in 2 suffix again too. So that's significantly small value. All right, we're going to do more questions about like those, dealing with some pKa, Ka later on too. So let's move on to exercise 9. Some theoretical, some theory-based questions. Oh, no, not yet. 9. Been a while. Been a week. neutralizations again too. Make sure you remember the assumptions. Assumptions that we take the mixture, the system's density as the water. So if you're given the grams, volumes, we take that as 1 gram per 1 milliliter. We also use the specific heat of capacity of the water too, which was 4.18 times 10 to the power 3 joules per kilograms per Kelvin, which is given on your formula sheet, as we discussed that too. I'd rather use that value you're given in the formula sheet to minimize any silly mistake. Okay. Or if you're confident, if you're like 100% sure, then you can use your own kilojoules if you like to. That's fine. But you won't get mark deducted because of you use a different some values of the C. Let's do it. 40 mils of the solution hypochlorite acid, HClO4, was added to the neutralize 40 mils of the 2 molar sodium hydroxide. The temperature of the mixture rose from 22.3 to 35.2. So in this case, we're assuming that everything got neutralized. We have no leftover, maybe with some, but we just take that as full neutralizations. So A, write a balanced chemical equation for that. So HClO4, aqueous, reacting with the sodium hydroxide, NaOH, aqueous. We do not put the double errors for the chemical reactions, by the way. Unless you have a reaction between weak acid and weak base. As long as you have a strong acid and base involved in your chemical reaction or the reactant, it always be single error. Why? Because that's a strong 100% dissociation. You're working 100%. So never ever put the double errors. I saw there's so many questions. People like, oh, we have acetic acid. Why isn't it double errors? If you have a sodium hydroxide, the strong base, it must be that. It doesn't, regardless of the weak acid. Okay, so what we get: sodium chlorate, ClO4, aqueous, and the 1 water formed like this. Everyone good? That is the balance equations. B, calculate the enthalpy of the neutralization for this reaction. So let's write it down, all that relevant information we have. You're given that the volume of the hypochlorite is given as 40 mils. Okay, maybe if you need to, but let's say the volume of the sodium hydroxide, or let's do this straight away. So to save my time, so your time too, is CV straight away. So 2 times the 40 mils, 0.04, gives you 0.08 mole per liter. Sorry, mole. What am I saying? Mole. Okay, that's the amount given. Then, according to the reaction ratio of the sodium hydroxide to water is 1:1, and H2O would also be same as sodium hydroxide, that is 0.08 mole, given as this. Okay, make sure you put all the relevant working out. After we got it there, we're given the Q. So mass of the, okay, in this case, it's not a mass of the water for the Q equals the MCAT. Remember that that's a different case scenario of the combustion. In case of here, we have taken the mass of the whole mixture, as because all rise, temperature, everything. Mass is from the total volume. That, remember to mix the 40 mils plus 40 mils gives you 80 mils. That's equivalent almost like 80 grams. Okay, or saying this is the same as 0.08 kg. C, assuming the C, so let's write like a full working out. That's what I really do in the exam. Assume that the system has the same specific heat of capacity of the water, that C is then equals to 4.18 times 10 to the power 3 joules per kilograms per Kelvin, like this. Okay, and change in temperature, that's given as T final minus T initial, showing the working out, 35.2 minus 22.3, 9,422, 12.9 Kelvin. Yep, everything good at this stage? Then Q equals to MCAD, that is 0.08 times the specific capacity, 4.18 times 10 to the power 3 times that 12.9 as that. So you get 0.08 times 4.18 times 10 to the power 3, that times 12.9, you're to get 4,313.76 joules. Now this must be converted into kilojoules again, so that's same as 4.31376 kilojoules. And that's what I mean by, like, I don't mind to see, like, if you converted the units from joules to kilojoules before that too. So it'll be the same as 4.18 kilojoules per kilograms per Kelvin. Okay, but it doesn't matter as long as you get this one right here. Then what's next? Delta H of the neutralization. Remember that this is always be an exothermic, or you can determine whether this is exo or endo from the change in temperature. It rose up the temperature from 22.3 to 35.2. So this is evidence that heat is released. Therefore, delta H must be negative in this case. Okay, that is Q on N of the H2O. That is 4.31376 kilojoules divided by given amount of the moles. Not this kilograms, it must be 0.08 moles. Make sure you use that, 0.08. Mole given, sorry, that divided by 1,000 and 0.08. You should get minus 53.922. Let's change that to the given sig figs. How many sig figs are we given? 3. So given 3 sig figs, this is the same as minus 53.9 kilojoules per mole. So delta H newt is this final answer. Again, exact same working out, exact same procedure like I showed you before too. I mean, so don't get afraid of dealing with those delta H newts anymore, please. One more thing. Do not get confused to, like, combustion. Okay, combustion requires we have a burner, and on the top we have a water there. This is the combustions. For this experiment, you had the last question from your homework too. We use a calorimeter and mix that solution in, and so this is the main difference between two. 13. Why can the hydrogen ion and or proton be represented by hydronium ion when in solution? Okay. A little bit of a theoretical, like some understanding required about, it's been a while, intermolecular forces. Okay, quick revision, just quick revisions. I just did the intermolecular force in my year 11 actually. This day, okay. Anything with the intermolecular, we'll probably do it again in module 7, but it's good to know now. Okay, we only have 2 types of intermolecular forces, 2 types. Okay, one is the weak dispersion. That is known as the temporally polar. From there, kind of when they're rubbing it, they get some temporary attraction. Okay, or the strong, known as dipole. Okay, inside of the strong dipole, hydrogen bonding is the special type when the hydrogen forming bonding with the oxygen, nitrogen, and fluorine. Okay, this is the strongest among the intermolecular forces. So, thinking about meaning of inter again, we kind of did that when I described the solubility before too. I hope you remember that. Okay, that water molecules, it's not the bonding between oxygen and hydrogen. Yes, we said that it's a hydrogen bonding, but I don't mean that. This is the hydrogen bonding. That's not a hydrogen bonding, that's intra. Which means happening inside of the molecules. I named that as, probably know that, is known as polar covalent bonding is the intra. So the extra bonding inside of the water molecules known as polar covalent bonding, which induces, due to that electronegativity difference between oxygen and hydrogen, induces partial positive, partial negative. That pair of the partial positive, partial negative is known as dipole. Two polarities there. So water is the molecule that carries the two dipoles in per molecules. See the two dipoles there, okay? Then what would be the intermolecular force? That means when we have another water molecule near at there will, due to the partial and partial negative, there will be really strong attraction between the hydrogen to oxygen. This is the intermolecular forces. So in between two molecules, interaction between two molecules known as the inter, and this is now, because they are so strong, they love each other due to that really strong positive and negative, it seems like almost like a bonded, almost bonded. So this is why I give it the name of the hydrogen bonding. So please remember that, don't use the hydrogen bonding to the polar covalent bonding. They're completely different concepts. Okay, why am I talking about these? Because I'm talking about, briefly about the oxygen, the water molecules, which is, because it has a dipole of the partial negative, partial positive, okay? So, and also thinking about the meaning of the hydrochloric acid, for example, aqueous here too. We discussed about what it means, the term, the state of the AQ. It looks like it's combined with the hydrogen. It doesn't mean that they are combined. No, it doesn't mean that. Okay, stands for the AQ means the hydrogen ion. It's another reason kind of separated with the chloride ions, forming some kind of like an ionic bonding, but they're not in the lattice structures too. So don't worry about the lattice for now. Okay, means they have a little bit being like separated to the chloride and the hydrogen ion inside like this too. Now, when then hydrogen ion comes along, it's very simple if you understood like some polar covalent bondings. Because of the polar covalent bonding, or because of the dipole of the water, the oxygen head, this positive charge will be strongly attracted to the negatively charged, which means it will get attached to the ore. And even look at the shape of the water, which is a bent shape. You would say the oxygen head is quite well exposed, kind of ready to, and it has also been lone pairs on the top here too. They'd love to, accepting the hydrogen ion. If you can imagine, like, oh yeah, of course, they can kind of expose. You can see like a bold oxygen. Oh, it's kind of exposed everywhere. Yeah, so hydrogen came along and got attached on the top. So forming what? Adding these two, there'll be a hydronium ion with the 1+ charge on the top like this too. So what's the reason why the hydrogen ion forms a hydronium ion? Because of the strong dipole of the the water molecules. The oxygen head will attach or forming the covalent bonding with the hydrogen ion. Therefore, easily form the hydronium ion itself. This is the easiest way I can explain you in terms of the positive and negative. Yes, I brought that dipole, I brought that intermolecular force. Chance of you getting questions like this in the exam, the HSC, it's low. It's really low. But it's a good revision that we are revisiting the intermolecular forces, all concept of dipole 2 or dipole 2. This will come again in module 7 and more dealt heavily. You will definitely get questions about intermolecular forces in your HSC. It's 100%. Okay, so this is the reason why when we describing the acid, we don't really say H+. When we are finding the concentration or the pH, we don't really say pH is equals to -log 10 of the hydrogen ion all the times. And this is the reason why I ask you to show that what happened to this when reacting with the water for the acid reaction. Okay, So just finish with this. When HCl reacting with the H2O water, that means that it will form hydronium ion with the Cl minus. This is called the what? The full equation, full chemical equations. But if I ask you to write it in the ionic equations, we ignore that, something in the comments too. So in the ionic equation forms, it will be this. HCl aqueous is actually forming that, the hydrogen ion and the chloro ion. This will be the ionic equation for the acid then. Okay, so ionic, which ions involved in the chemical reactions case. All right, so food for thought for question 13. 19, let's do that too. All right. I just can keep that for now. Okay, write an equation showing the dissociation of the calcium hydroxide in water. So calcium hydroxide, CaOH2, aqueous, reacting with the water, the liquid. Just bring back. Base is proton acceptor. Okay, base or hydroxide, base, proton acceptor, accepting proton from the waters too. For that, we need to have two of those. Don't leave the oxygen, by the way. It'll leave the two of the hydroxide as a result. Okay, or you can just think that it is some sort of the acid and base reaction too. Think about what happened. Calcium hydroxide now receiving that hydrogen ions. So forming that, leaving the calcium ion. Okay, also leaving what? This hydroxide will receive that too, so performing the 2 water. And leaving left, there's a hydroxide ion left from this water molecules too. Does it make sense? Okay, it looks like, oh, so what we can do, we can actually cancel this one out. Then you'd get calcium hydroxide 2 aqueous, forming that calcium aqueous and 2 hydroxide ion like this. To complete the balance equation. Okay, now, one question. Guys, what's the bonding between calcium and hydroxide? What is the bonding between calcium and hydroxide? Ionic. What's the ionic bonding? Bonding between metal and non-metal. That's a positive and negative too. Okay, so basically this is the same situation that you're dumping the metal and non-metal combination into the full of the dipoles, full of the strong dipoles of water. Okay, did we do that? We did in the solubility. What that means is the strong, there will be, remember the term? There will be dipole, ionic ion dipole interaction. Ion-dipole interaction will happen. So water molecule comes along, separating that. Yes, in the same time as separating the hydroxide ion, water molecule is actually kind of reacting with the hydroxide ion too. What that means is H2O comes along with the this is kind of combined there, and this is basically making another whole H minus and H2O2. Okay, so think about it here. We have a water where OH minus comes along. So OH minus looks like this. It has excess. Minus means having excess hydrogen. So excess of 8 electron there too. Lone pair with the 1 free electron like this. This is OH minus. Okay, when this comes along to the water, because of dipoles, it would take the 1 hydrogen away. So now it becomes 2 new water molecules. What about the leftover? It becomes the OH minus again too. So what they do is they're just playing around with the hydrogen ion. They're just kind of giving give and take of the hydrogen ions. So almost like, there's nothing really happening. Yes, there is something that's happening. You would see that this goes like a backwards too. Can move backwards too. Okay, but it's all because of that. I mean, this is actually for the students in university. They actually study that more in details too. You don't really need to know up to this stage though. But I want you to just imagining about what happens to when it comes along. And there will be what? The stronger ion dipole interactions, therefore, which is greater than the ionic bonding. between the what? The calcium hydroxide. So what do they result? They're resulting in that formation of the release of the hydroxide ion in this case. Using the bit of like some theories we learned in solubility again too. Remember that why the salt, so the sodium chloride solid dissolve in the water. We discussed that because of the stronger ion dipole interaction between the ions to the water, okay, ion bonding gets destroyed or kind of separated so that we see that hydrated salt. That's what we discussed before too. Similar things happen. The calcium hydroxide being H2 almost got to go. They're like it comes and goes, but almost fully separated and release of the hydroxide ion as a result of that stronger ion dipole interaction in this case. Okay, I just brought that back because I really don't want you to forget about some solubility. And in the worst case scenario, if you get questions like this, just try to use that definition and terminologies as you go. So dipole, again, ion dipole interactions. Do I have to explain that again? I hope not. I hope not, okay? I don't want to come back to the intermolecular force anymore. So I just want to go like, hey, remember intermolecular force. Why then our cores have this such a high boiling point? Questions like that later. Everyone good? Okay? Okay, what I'm going to do is, yes, I have an extra chapter that I made for this. Actually, let's try one more question. I'm going to skip it lots of pages because it's kind of same concepts that we went through, so, and I expect you to know that. Okay, let's do one more question. Or should I? No, I've got to do the HSC questions. Let's do the HSC. So pass that to, pass the one. Guys, that's collection of the all past HSC from 2000, maybe 18 till last year, 2023. Yeah, 4 years, up to 5 years worth of the HSC questions, only for these chapters. You have more for the rest of the chapters too. Okay, obviously, that's your homework. And you have extra homework as well too. I keep my promise. I'm asking you to do more work, so I'll give you work to do. Okay. Okay. Let's have a look at one of the questions in there. Okay. Just let me just open that. I would like to have a look at that question. Oh, damn! I actually needed to separate them, but they're okay. 22. I know we don't have a space for that, so. But I just want to have a quickly look at those questions. I will ask you to do a few here. This is 2019 HSC question 33. Okay, so a student adds 1.17 gram of the aluminum hydroxide to the 0.5 liter of the hydrochloric acid. Calculate the pH of the resulting solution. Assume that the volume of the resulting solution is 0.5. Did we do that type of question today? I did that in the beginning of the class today, and I didn't make it. HSC. This is what I mean by you sometimes get a basic questions that we studied in here. So, guys, this is one thing. Please don't ask me the basic, the simple, the fundamental questions whilst we're preparing the HSC or trials. Okay? This is why I ask you to do it now. Okay? So that's, I'm going to skip down, by the way, and I assume that you know how to do it. So answer that in a separate page or separate notes if you can, because you don't have a space. You will get, okay, what I'm asking to my markers, and if I'm marking yours, we will actually give you marks out of 4. You will get a marks for 4 out of 4. So if you only write the answer, just the answer, I'm sorry, 0, even though the answer is right. I need to see the working out and follow the template that I explained today. All right. What I'll ask you to do is, so acidic and basic. Question 24, please. I'm going to answer this question together now. Methanoic acid reacts with aqueous potassium hydroxide. A salt is produced in this reaction. Okay, this is a bit of a combination to the little bit of the module 7, so this is why I brought this question. So methanoic acid is something that look like, Judy, it's been a while. Meth, see, they look like this, COH, and meth having just one, so only one carbon. So it would have hydrogen like this. This is a methanoic acid. Don't worry, I will teach you how to do this in module 7. You will ask to memorize everything, isn't it, Judy? So CH or CH or OH is known as methanoic acid. Okay, or HCOOH, that's the same thing. So that aqueous reacting with the potassium hydroxide, KOH, the aqueous, this is producing that. Okay, even though we're using the organic chemistry, organic acids, it still be acid and base, proton donor, proton acceptor, which means resulting in CH, KCHOO, just like acetate, and then leaving that water, H2O liquid. Nothing really fancy. Balanced? Yeah, it is balanced then. B is the salt. So what's a salt? Salt that's produced is potassium acetate, potassium methate, known as. Okay, this is a salt that produced. Questions asking you whether they're acidic, or basic salt. This is not in your the workbook. I actually forgot to put it there, so I just explained it in here. Just remember that. The way we can determine the acidic, so whether that salt is acidic, basic, or even neutral is, you have to put the salt in react in the water, okay, and determine the what do you call it, like their products, to decide to classify that whether there's acidic or basic or neutral. So for example, potassium methate, the K, CHCOO, aqueous, reacting with the water. See what is happening. Do you remember the conjugate acid and base pair? We're going to talk about that too. So when these two are reacting to each other, first, what happened? It's producing that. The hydrogen ion will be replaced, so produce CHCOOH. Again, aqueous. Okay, and the leaving what? Leaving the potassium K plus detached, and with these some OH minus like that. What you see in there is from the salt, it's actually producing that acid. Again, I mean hydroxide is the form that actually produced kind of detached from the water, and acid, and that's the base. But considering that, if this is the weak acid, there's a weak acid. Can you see that? Okay, as it's producing back, it's a weak acid produced, and instead we have the potassium hydroxide or the hydroxide. It's kind of produced. Now, I just want to think about the mixture here. We mix the salt into the water. Okay, it produces some salt. It produces some weak acid with the some amount of the hydroxide left over here like this. So what is this? If you find the pH of that or pOH of that, I would expect that it has a certain pOH value. Okay, so making that what? Made that solution to be basic. In this case, we call this as our basic salt, alkali salt, from the presence of the OH minus there. Kind of confused? Yeah. So it's important that what we put in, so acidic salt. So let's show the one example of acidic salt. For the acidic salt and the basic salt, I will actually spend more time to next week because it is something that's very important. And as you can see in the HS question, you get that quite often too in the multiple choice. So I'm going to spend a little more time on that. But just remember that this is something that we're dissociating to determine that whether it's acidic or basic. All right, the question that I want you to do is this. Next one, 25. This is 3 marks. So I give you 5 minutes. One more minute. Three. Too easy. I mean, I did that, didn't I? I even warned you that, yeah, we had a question in HSC. Okay, let's see how many these type of questions that we had. Sorry, I skipped that. 25. This is 2022. I was okay. I'll show one more. The same. Page 19. That's last year's exam. So pH of two solution X and Y is given that. You have that. That's two. They changed a little bit format, but these two in 2 years are the exact same questions. I mean, what I mean by that is now where you answer this question is exactly the same. That's a high percentage, isn't it? Out of 4 years, you had 2 exact same question styles. Okay, you may not get the same exact style this year because that's from last year. Last year in 28th of the October, by the way. So by the time 28th of the end of October, you will get the HSC chemistry. Yeah. So let's have a think about here. This means that if you can answer that question from 2020, 25 again, question 25, 22, I'm sorry, 2 years actually, 2 years in a row that we had the exact same type of questions too. The way you need to think about the question is first, I have hydrochloric acid, which is, I'll ask you to memorize it. This is a strong acid. Besides of the older 3 strong acid, what are they? Hydrochloric acid, sulfuric acid, nitric acid that I'll ask you to. Besides those are more likely to be a weak acid then. Okay, so what is the question? You need to understand the purpose of the question, what the examiner is asking you. This is asking you, hey, tell me about the difference between strong acid and weak acid. Yeah, and it's not a calculation. You may need to do a little bit of a calculation, but this is more about explanation questions. Tell you, 3 marks. Average, the mean marks was 57%. What that means is average was something like about 1.6 for this question. And 2022 paper was known to be pretty difficult. The raw mark to get a band 6 in that year was 79. So if you get like an 80, so you got a definite band 6, or like a 90 in your examination mark in that case. For 1.6, yeah, that's quite disappointing, by the way, okay? But not for my students, though, okay? Because I'm doing these questions again, too. All right, you have given read the question very carefully. You have the same concentration of 2, but kind of really different, like a huge difference of the pHs. So explain why the HCN solution has a higher pH than HCl solution. Include any relevant chemical equation for the HCN solution. Okay, so let's talk about it here. First, you need to talk about the hydrochloric acid is a strong acid. Do you think we need to define what the strong acid is? Yes. Not because like the examiner marker doesn't know what the strong acid is. This is how you get the mark. This is definable as what? Means that ionizing or dissociating the full 100%, or sometimes you can say fully dissociating, fully ionizing. Same thing, okay? Just 100% fully dissociating too. Or you can say release fully releasing the hydrogen ion to where? In water. And you might need to show this. Oh, how will you show that? Hydrochloric acid, aqueous, reacting with the water, liquid, goes one single arrow, as I said before, okay, producing the hydronium ion plus the chloride ion like this. That's simple. the single arrow representing that it's a strong acid. Okay, 2. Cyanuric acid is a weak acid. By the way, yes, I'm writing the dot points, but it doesn't mean you can write the dot points in the exam. Just write the sentences, or just connect them to. Okay, I'm just showing you to give you a better picture or some structure of your answer. So HCN is a weak acid, means that this is not fully just following the same definition, releasing the hydrogen ions in the water. So in this case, hydrogen cyanide acid reacting with the water, it will be a double arrows because the weak acid and release some portion of the hydronium ion and some portion of the cyanide ions like this. Okay, now, and the questions are also asking you this, hey, then why would they have the different pHs, even though they have the exact same? So for hydrochloric acid, let's have a think about it here. The pH is calculated by minus log 10 of the hydronium ion, or same for the minus log 10 of the hydrogen ion. Doesn't matter for this. Okay, so for HCl, okay, the hydronium ion concentration must be exact same as the concentration of hydrochloric acid. We define that. So it makes sense that therefore pH must be minus log 10 of the given concentration of the 0.2. You might get the 0.7 without doing calculations. Yeah, because that's theoretically right, and if you calculate that, you get it right here. And this representing what? It's due to the strong acid, or sometimes you can say that due to the big Ka value, if you'd like to say that, but that's fine. Okay, so this is the pH when everything is getting dissociated. Okay, but for CN, HCN with the same concentration of the hydrochloric acid. Okay, what happened here is the H3 or plus. Do you think would it be same as the cyanide concentration? Would it be actually less? Does it make sense? Okay, due to the lower concentration of the hydronium ion in the HCN, running out of ink, pH of the HCN is lower than the hydrochloric acid then. What does the mark? How do we mark your works? We're seeing that whether you complete, whether well define the strong and the weak acid as 1 mark. Definitions of the weak and strong, 1. Show that relevant, even say it in the relevant chemical formulas, equations, would it be 1, 2? Okay, showing that some proof that 0.7 calculations, and this is why this is a strong acid, or using any of the definition of pH. So using the definition of pH to describe the differences of weak and strong acid is 1 mark, which means you might need to show the calculations to find the pH of this hydrochloric acid, because you can't do the same thing for the weak acid because we don't know the Ka value. And the question is about using the Ka. Yes? Oh, sorry, the higher then. Sorry, my bad. It would be higher. Higher than hydrochloric acid. Why am I giving you some kind of template for this question? Because let's revisit that question you had. 33, if I remember, 34, 5, okay, 35. 2023, question 23 last year. Yeah, I mean, you can check that. This is actually HSC question last year. Okay, you see that the pH of two solutions X and Y were measured before and after 10 drops of the concentrated sodium hydroxide was added each. 3-mark question. Explain the pH changes that occurred in the solution X and Y. So what we have is X and Y. We don't know whether one is which is which. We don't really give any of those, like an acid, the acid type. But what we know here is that, so the reaction between sodium hydroxide to solution X increased the pH to 12. This is actually a buffer question, I'm sorry. It's a buffer questions there too. But you can think of it here. And this question only increased by 2 over here. So you got to talk about the property of the strong base that's fully ionizing that too. Sorry, this is actually a buffer question. It's not exact same question styles. I'm sure I have the questions that are attached before. Maybe not. Maybe I was wrong. I saw there's so many questions about it before. Maybe the multiple choice. Okay, there we go. Question 13. Just have a look at the ground on the board there. Which beaker contains a concentrated strong acid? Again, this testing new with using the definition of the concentrated and strong strength and the concentrations. Concentrated means what? Remember that it all simply means the quantity, how many we have. But then how do we know something is a strong acid? The fully ionized, it means that they're all detached. You shouldn't see anything that's combined too. So the answer, if you understood that, the concept of the strong and the concentration, then it's definitely D is the answer straight away. If you understand the content, how long does it take? 5 seconds? Really? Yes. As soon as you look at the question and the answer, like, D is the answer. You don't need to look back. You don't need to recheck these kind of questions again too. Remember that per mark in the HSC means you have a 1.5 minutes. If you only spend 5 seconds for this, you say like good like a minute and two sometimes. That's how you need to solve the question. You don't have to spend 1.5 minutes. Okay. Let's do one more. I'm sure we have one more question related to that. Question 1. Which diagram represents ionization of the weak acid? 2018 HSC question. The multiple choice. What you see there is the water molecules, the weak acid. So, give you 10 seconds to think about what would be the answer, considering what I mean by the weak acid. 5, 4, 3, 2, 1. What is the answer? Could it be C? Got it? You get what it's a C? It's a weak acid, by the way. It's not a concentration anymore. Weak means partially dissociating. How do you know it's a partially dissociating? We still see some are now attached as the forms of the acid. A is what? A is strong acid. That's fully ionizing. See, this is how you get in your HSC questions. So if you get questions like this in HSC, the chance you get that in trial exam, I would say really high, 100% every year. Okay, so that's the type of question there are one thing. All right, so page 12, question 28. How many marks? The 5-mark questions. I'll give you about 6 minutes for this question then. Try it.